Hey everybody, G. Smith here from the DiagNation studio and labs here in the great state of Maryland. I'm really excited to be with the WMDA crew today. This is a fantastic opportunity to get together and discuss some really cool technology that's showing up in our diagnostic bays. I'm really excited to be with you today. Lots of web stuff going on, and these WMDA Lunch and Learn Tuesdays are a fantastic thing for crews to be able to sit and have a lunch and pick up on a good subject. So anyway, welcome. Thank you so much for being here today. My name again is Gary Smith, and we're going to get into pulse width modulation here. Now, just as a matter of housekeeping, typically when I run a web class, what we'll do here, we've got about an hour. I'll probably just continue to teach. We're going to try to field some questions. I see one here. Let's see, are you guys hearing me? Can somebody just let me know if you're hearing me, because somebody says no audio and I don't know if that's on their end or my end. Can you guys hear me okay? And to answer Robert Miller's question, we will have a workbook available for this class. At the end slide, you'll see my email address. Fantastic. Thank you, Robert. I'm glad my audio is okay. So we will have a copy of the book for you guys. Evan Goodrow looks like he keeps saying no audio, but I believe that's going to be a problem in his computer possibly. But anyway, yes, at the end of the slide, guys, you will have a book or an email address to go to. Please email me your name and the class you attended today, and I will make sure that you get a workbook, okay, for this. And it will exactly match and actually exceed what we're able to cover in this 1 hour event, okay? So thank you for that. Now, related to the rest of the questions, if I have the question pane up, it's very difficult for me to see the slides and work, so I'm gonna put the questions down. I will stop every once in a while and take a look. And probably about a half hour into it, I'll stop and answer any questions that are there, okay? There is a lot to cover here in the next few minutes, so we're going to get right at it, okay? Now, what we're going to cover today, guys, is pulse width modulation, and we're going to cover pulse width modulation from a theoretical standpoint and then work that into a diagnostic standpoint. The reason that this is important is that more and more systems on today's vehicles are utilizing pulse width modulation for a number of things. One is signaling. As we know, pulse width modulation is used back and forth between the computer and different sensors on signal lines. But what we're going to concentrate on today is the use of pulse width modulation for controlling power control circuits, motors, steppers, throttle motors, that kind of thing. But pulse width modulation is used in all kinds of automotive systems, all through the vehicle, in the chassis, in the body, the airbag system, with literally everything you can think of, right down to the heated seats in today's modern day cars are pulse width modulated power controls. So what's really important about pulse width modulation is, if we can understand the signaling aspect of pulse width modulation and how the PCM is actually putting together, monitoring, and adjusting that signal, we can then transfer that theory over to the power control side, where the beautiful thing for us using lab scopes for diagnosing these systems, ladies and gentlemen, is that the signal itself is the power on the device. And that is a beautiful thing, because in that sense, oftentimes we can look at the output device, the circuit, and the PCM all in one screen to make a determination as to what's wrong in the circuit. So what is modulation? Well, modulation is simply a method of transferring signals or control voltages and current to run output devices via what they call a signal carrier. Now, the signal carrier is modulated in such a way as to basically convey some type of information, okay? Now, typical automotive signals that are modulated are going to be the analog, and believe it or not, about 99.5% of all the work we do in automotive chassis and powertrains is going to be diagnostically in the analog realm. We always like to say we work on high-tech computerized digital cars, but as technicians, we don't work on the digital part at all. Meaning the digital part is what's going on inside that box. And because of microcircuits and microboards and IC chips, the average automotive technician has zero interaction with the electronics or the digital side of that car. We live in the analog realm, but we are translating, tracking, and hunting down problems in analog circuits that carry digital information. That's the important distinction to remember for the diagnostic side of this class, is that they're one and the same in most cases, especially where we're pulsing modulation to a heated seat. So we've got a short pulse period for the low setting and a full-on high pulse period for the high setting, where it's nuking your backside as you drive down the road, right? So there we have a digital or mixed signal coming out to us in our scopes and our meters and our scanners in the analog realm, right? Very important distinction when looking at pulse width modulation. Now, what kind of different signals are modulated in an automotive chassis? Well, we certainly have RF or radio frequency signals, okay? That's basically any signal that's going to exceed 30 kilohertz. There are several radio frequency type signals or radio frequency speed signals going on in an automotive platform today, especially when you consider ADAS and telematics, radar, cruise control, DSRC radios, all these kinds of things, TPMS, quite frankly, okay, that's sending radio modulated signals out of the sensors and into the TPMS module in the car. So we're also modulating audio signals, obviously, right? We've got dings, beeps, chimes, radios, music, human voice, audio, all of that integrated into the car. We have to be able to understand how that's modulated. And I'll tell you this, my experience running the DiagNation support is that more and more technicians are having to get themselves involved in AC current frequency, audio frequency and radio frequency diagnosis and understanding. See, this is where we depart from 12-volt DC electronics. And in systems such as the ones we're going to cover today in the fuel pump area and the, say, Valvetronic motor area on, say, a BMW, these are where technicians can get in trouble because they're expecting DC grounded operation, and what they're seeing is AC frequency waves controlling that system. Really, really different than what we're used to in our industry. So that's why we put this class together to kind of get the idea together here that we've got logic, we've got analog, we've got audio, RF being modulated, RF radio frequencies, we've got signals from sensors, we've got what we call mixed power, which is what I was mentioning to you at the beginning, which is for your fuel pump control or your throttle motor control or something of that nature. What you're going to see there is that the digital signal coming out of the computer is the power that runs the device, right? Now, the other thing that's very interesting when we say a signal is modulated onto a carrier line is the concept for automotive guys of a bias signal line. A bias signal circuit actually is a pretty complex circuit. Some of us understand bias to a certain level as it relates to maybe an oxygen sensor or some sort of other sensor circuit in the car. But I'm going to dial in, hopefully, if we have time, a little bit on bias circuits so that we understand that the bias itself is the signal carrier in the case of a PCM bias circuit for, say, CAN bus or some sort of circuit like that, right? Then the other thing that we've got going on in modulation world today is software defined radio, okay? And that's transmitted all through the car, all the way through the audio circuits related to the DVD players maybe in the back of the car, all that, right? And then the biggest one that we're modulating and tracking modulation on when we're looking at those pretty packets on a scope is our network analysis, okay? Where we're looking at an analog translation of a digital modulation on a biased line. So this is where some of pulse width modulation theory comes in handy to understand that circuit that we're looking at. So as you can see here on the slide, guys, lots and lots and lots of modulation is going on in these vehicles. Now, in the modulation world, we've got 3, 5, 6, 10 infinite methods of modulation. We could go on and on with slides on this from an engineering standpoint, but the main ones we're going to see in a vehicle are going to be FM and AM, obviously. Okay, digital baseband. Okay, we use a lot of digital baseband logic in network transmission today within vehicle platforms. Pulse width modulation, as we're discussing today. But another one that's becoming very common in European cars and other types of encoded sensing applications is going to be the PAM, or pulse amplitude modulation, right? So we have pulse width modulation and we have pulse amplitude modulation. These can be combined into what they call encoder units, or encoder modules and encoder motors. So this is a very complex thing to diagnose beyond the power and ground aspects of whether our circuit is functioning, right? And then, as we talked about, automotive domains utilize this kind of modulation in literally just about every single system in the vehicle. So how do we test and analyze pulse width modulation? Well, in order to understand that, we really need to understand how pulse width modulation is actually built and generated within that magic box, the PCM, or that module, whatever it is we're working on. So there are some basic pulse width modulation circuit components that are used to generate this kind of signal and control. Obviously, we've got a microprocessor, we've got a chip. Okay, that chip is very important, and I've got a graphic here in a few more slides that we're going to construct an oscillating pulse width modulating circuit so that our brains can get our head around what we're physically measuring with the scope on that car. We're also going to use lots of transistors in a pulse width modulated circuit. The output for that pulse width modulation, whether it's the actual power control through a MOSFET device or some sort of FET device, or whether it's transistor logic or CMOS logic, is going to be transmitted through transistors. So that's a major player. And for those of you that are looking at studying electronics and electronic controls further, definitely get your head into that transistor, because that transistor in the car and in those modules is used as a switch, an amplifier, an oscillator, all kinds of very important technical concepts that need to be understood with transistors. Certainly not enough time in this class today to cover that, okay? We'll cover a little basics on it in the next couple slides, but that's it. Now, what we're going to do with resistors in the chips, or transistors in the chips, is use a combination of resistance and capacitance to actually trigger the circuit on and off based on what the logic is telling the chip to do. And that's done with a feedback, as you'll see on a concurrent slide here as we draw out the oscillator to make that thing work, okay? Now, in addition to the resistors and capacitors, we're also going to use inductors to control current in the pulse width modulation scheme, right? Also, we're going to discuss flyback voltage schemes. Flyback is the voltage and the current that is thrown back at the driver of the circuit that's being operated. For example, an ignition coil, an injector, or a fuel pump module, or a Valvetronic motor, or something of that nature. And that reflected energy is what literally takes out the driver and destroys the inside of the PCM. So we'll touch on that a little bit to understand how to look for that flyback on a scope. Also, just a little bit of coverage here when we actually draw the oscillator on diodes. Okay, diodes obviously being a one-way valve. That's a very important thing in controlling that flyback from that ignition coil, injector, or motor. So all of these things conspire inside that box based on mathematics and engineering to come up with a circuit that is going to use a logic signal to control an output device. Now, the modulation itself is basically a time-controlled method of switching or cycling current and voltage to an electrical load or from an electrical load, including things like sensors, solenoids, motors, stepper motors in the case of